Hi everyone, my name is Daan. I'm here from the Eindhoven University of Technology to talk about algorithm support directly inside of Graaf databases. I'm going to focus on three things. I'm going to discuss why we need algorithm support integrated into Graaf databases. I'm going to talk about our proposed approach for doing that, which of course is the right approach. And I'm also going to discuss some of the key features of our system. So just to start off with me, because I think most of the people in the audience don't know me yet. I'm a first-year PhD student at Eindhoven University of Technology in the database group, which is led by George Fletcher. My supervisor is Nikolai Jakovets. Those are names that you might or already know. My current research focus is on algorithm support in Graaf databases. That's what this talk is about. But more broadly, I'm also interested in query processing, hardware acceleration, and compilers. I also like cooking and baking when I'm doing research. We are actually hiring a lecturer position for a lecturer position at our database group right now. So if you'd like to try some of my pastries, you should apply. So nice to meet all of you. Let's get to the topic of the talk today.
Then can I interrupt you a little? Can you get in position? Are you able to do that?
Yes, I could. Yeah.
Yes, please. Yeah.
Yeah. Okay.
Yes, because the people is asking about that. Yes.
Yeah.
Sorry.
No, that's all right. Sorry, do I need to have anything? I just need to join. Right?
Yes.
This. Okay. Like this.
Yeah.
And I can. This is all fine. Like I don't need to do anything.
I think.
Or do you want me to share the screen?
Yeah, sure.
Okay. Yes. Yeah. Sure. This should be fine.
Yeah, I think.
Right. Thank you. So we're good. Yeah. Just to check that my clicker is still.
That you're sharing? Yeah.
Yep. Okay. Perfect. All right. Let's carry on. So carry on with the talk. So with the rising popularity of Graaf databases, what we're seeing now is that there is a great variety also in workloads that are popping up. So you can go from very simple queries, things like simple local lookups, like give me all the neighbors of a particular vertex, like this is the simple stuff. We're also seeing much more complicated queries. So people want to run full-scale algorithms on their data, things like PageRank, connected components, and we also want to cater to that. And what happens is as you go from these much simpler queries to much more complex problems, you kind of move here on the expressivity scale because you require more expressive languages to encode those algorithms in. And as the expressivity increases, you naturally also make the job of actually optimizing such queries and evaluating them significantly harder. So to talk about these graph query languages we already have, there's things like Cypher, we have GQL, we have a presentation about that today. These are great for sort of the simple stuff, right? You can do subgraph matching, you can do even some navigational things, but they're still a bit too limited if you want to really do graph analytics. So you can't write in Cypher a PageRank implementation, for example. That's a problem because people still want to run PageRank on their data and other algorithms. So naturally, people are going to find some kind of solution to do it anyway. And actually, a very common approach now is that people will give up on the Graaf database and they'll say, you know what, I will just dump all of my data out into a CSV file. I'll import it in Python and just do it there. Do it in NetworkX. This is very wasteful for a variety of reasons. If you have a 1 terabyte database, you're going to end up with a huge CSV file, which is going to take ages to create, convert, and import. You're going to duplicate all of your storage, and you're also losing, for example, all of the statistics that your database only keeps about your data to make your queries faster. So obviously this is not great. I'm not the first one to realize this. Like Graaf database vendors have also noticed this, and they have been looking at implementing algorithm support in their offerings in some shape or form. So just a quick overview of what that looks like today. You can go a few ways. In the Graaf space, what I've seen is that a lot of vendors will give you a fixed set of algorithms. So they'll implement a high-performance version of common Graaf algorithms, and they'll ship that as something you can kind of invoke from your query language. that's nice, but it does limit you to just that set of algorithms that is supported. So if you need a completely different algorithm, or if you need even a minor variation of an algorithm, then you're out of luck, and then you cannot use any of this. So there are also some more flexible approaches. I've seen multiple vendors offer a Pregel API. So this is kind of a vertex-centric processing API, and this would allow you to construct your own algorithms. That comes with its own issues, though. I've noticed some performance issues in these implementations. And you also lose analyzability. And what I mean by that is that when you use an API like this, in this case, it tends to be a Java API, that's not the code that you write is not something that a query optimizer can actually look at and inspect and optimize in any way, which of course is detrimental to performance. So that's a big downside of this approach. Looking at the relational world, there's also some interesting ideas. The Umbra people, they came up with this concept of a user-defined operator. So then you can actually, in C++, you can write your own query operators, and that can be integrated into query plans. That gives you really excellent performance, but you're writing this in C++, right? So if you put a bug somewhere or some illegal memory reference, you're going to crash the entire database system, which for a business perspective is usually completely unacceptable. And it's C++, so again, you're losing this analyzability property that graph query languages usually have. In a more traditional, for the more traditional options, you have things like recursive CTE. So you have recursion support in many SQL databases. That's very powerful, but these queries tend to be very, very difficult to write. And in my experience, they also come with significant performance issues. What you also get is some vendors will give you extensions to SQL that add procedural things like loops. That's very useful. It's much more user-friendly. But usually query optimizers also don't really look at that. They will just optimize the individual SQL statements that you put in these procedural languages. So that also leaves much to be desired. And these interpreters, they tend to have tons of overhead. So then we get to the last option, which to me seems like the best approach. Like this will give you, so this is a DSL, a domain-specific language. So in that case, the database will provide you with some language that you can then express your algorithms in a user-friendly way. So this is nice because for users, they have some interface that is kind of intuitive to work with. And if you do this right, then you can still get, then you can still have a query optimizer actually inspect this language and optimize it in some way. So unfortunately, the implementations I found, some of them are Graaf and PGX, which we've heard about earlier today. They're all proprietary. And usually their integration with queries is not great. So I know PGX, for example, keeps sort of their algorithm execution completely separate from the query execution. So it's completely separate pipelines, and there's no mix or match kind of thing there. So that's all a lot to take in. So I'm just going to summarize this a bit for you and say, what should this algorithm support look like, in my opinion? First of all, it should be flexible. So you don't want to be limited to a specific set of algorithms. You want to be able to have fully custom algorithms that users can provide. So they don't need to escape into Python to do things. You want this interface to be reasonably intuitive so that people can actually use this, have a clear and convenient syntax. You want it to be fully integrated into the database. And by that, I mean that algorithms should be first-class citizens. So I don't want this algorithm processing to be a completely separate thing. I want to reuse as much as possible of the existing query processing infrastructure, use that stuff to do algorithm execution in. And also allow mixing and matching of algorithm queries. And lastly, we want to be able to process very large graphs efficiently with these algorithms. So we want to be able to analyze and optimize our algorithms in much the same way that we do for queries. So can you guess what my next slide is going to be about? Introducing Graaf. Graaf is a language which is purpose-built for writing graph algorithms. It is directly fully integrated into the Daan graph database system, which we're developing at our group at TU Eindhoven. it's designed such that it's highly optimizable. So this is a language that a query optimizer can actually look at, inspect, and analyze and transform in non-trivial ways, much like queries. And what we also do is we allow such algorithms to be embedded into cipher queries, actually. So we have a little bit of extra syntax here, and then you can just write your algorithm in this Graaf language, and that can be embedded into queries, and that's executed and optimized together as one component. To give a bit more details about what this language sort of looks like and feels like, some key features. The main discussion point for us was what computational model should we use? Because there's been various proposals in the existing literature. I've already discussed sort of Pregel style APIs. This is what is called vertex-centric model. So this is where you write a little program that runs basically on every vertex of your graph. There's the vertex and edge sets model, where you sort of collect sets and sets of vertices and sets of edges, and you process them in bulk, typically with explicit parallelism operations. But for us, we found linear algebra to be the right sort of fit for this purpose. The reason for that is that, first of all, linear algebra operations, they're quite high-level operations. They operate on entire matrices at a time, and this makes them intrinsically parallelizable. Very useful for performance. Linear algebra is something that is very widely taught in many engineering disciplines, not just computer science. And what that means is that people already know the semantics of these operations, and they're widely taught and understood. So this also lends the language a sort of easy entry for new users. I'm not the first person to look at linear algebra when I want to do graph analytics. This actually is a proven approach. You can buy entire books that are dedicated to just this topic. And there's even an open standard for primitives for writing graph algorithms in the language of linear algebra. This is called Graaf. So just to look a bit more at the linear algebra and the internals of the language. So we provide, of course, the Graaf language. This is quite a rich language, which makes it very easy for people to implement a wide variety of algorithms in it. But next to it, we also provide what we call a core language. And this is basically a very small, reduced set of Graaf with just the minimum set of operations that are necessary to preserve the same expressiveness. So actually, the full Graaf language can be reduced just to this simple core. And that core language turns out to be, well, it's not a complete coincidence. Is equivalent to a language called MATLAN. This is a formal language for matrix manipulation. It was proposed a few years ago. That lends the language also its sort of solid mathematical foundation. So we have a sound type system, we have operational semantics, and all of this which is based on this existing MATLAN language. You can see this as a sort of more as a practical first implementation of this theoretical one. And what we add to MATLAN is a novel concept of loops. This is necessary for iterative algorithms such as PageRank. And what we try to do there is we try to strike a careful balance, right? We want to give users the expressivity that they need to be able to express a wide variety of algorithms. We want it to be as restrictive as possible so that our optimizer is free to perform a lot of rewrites. This core language also ties into sort of our compiler for the language. We start off on the side there with the full Graaf language that is then reduced into this core language, which is basically MATLAN with a loop construct added to it. We transform that to an extended relational algebra, and then it can be integrated back into the query. So that already gives you a pretty clear idea of what the compiler starts to look like. So to give a bit more details on that one, what we have inside of a Van graph is a unified IR. So that means there's a unified representation that can encode both queries and algorithms. So we take the original queries and the original algorithms, we convert them into this unified representation, and then that completely eliminates actually the boundaries between query and algorithm. They become one single thing. What that allows you to do is to perform optimizations that are not possible just on the query or just on the algorithm. you can actually perform optimization across this boundary in very complex ways. And after this unified error, because there's no more difference, we actually have a unified optimization and execution pipeline. So any optimizations that are available to queries, they're also immediately available to algorithms. And there's no runtime cost to exchanging data between query and algorithm because they are one and the same thing. I want to touch a bit upon how we evaluate our system because this is the LDBC meetup, and I'm glad to say that we actually depend on some of the work done here. So we use the LDBC Graphalytics benchmark suite to test our implementation, basically in two ways. First of all, it's a measure for us of expressivity. So the Graphalytics benchmark gives you a set of graph algorithms, and by showing that we can actually implement all of these algorithms in GraphAlg, this gives us some level of confidence in the expressivity of our language. Of course, we're not just limited to this, like we also implement, for example, algorithms from the GAP benchmark suite, but having this Graphalytics set of algorithms is very useful to us. And of course, the main reason we use it is also for performance, right? We use the data sets that are the synthetic and real-world data sets provided by the Graphalytics standard. And there we compare our system to the existing reference implementations and Postgres and GraphClass. And we've also added to that a driver for DuckDB, so that we can run the algorithm on that system. And we also add support for the Neo4j Spraggle API. So I will conclude with the implications of this work. I believe our work represents a significant jump in the programmability of graph databases, that we can finally run actually algorithms directly inside of these systems. And what that does is that it kind of blurs the lines between graph databases and graph analytics frameworks. Our system actually provides very similar functionality to a graph analytics framework, but with a much more intuitive, easy-to-use language, while retaining excellent performance. And I think what this shows is that we should look at graph databases not as tools for answering simple queries, but we should start to look at them like platforms for efficient and large-scale data analysis. And with that, thank you.